Okay, so morning, welcome. It is September 15th, and we just had a little discussion here with our face-to-face group about what we're going to cover today. Probably can't read it on the board behind me, but I do want to start off with a little bit of a quantitative discussion about Summary 1. I'm just going to discuss it in general, go over some of the things that were very, very revealing and mind-opening to me when I first read the thing, or wrote the thing. It took 4 years to write. I started writing it in 2004. It wasn't published until 2008. It's out there online. As I mentioned previously, it was it stirred a little bit of controversy with the Canadian Nuclear Commission. They wanted to use it to sort of show the superiority of nuclear fuel as a carbon-free source, etc. They claim to have found an error in it, and let's just look at exactly where that error is. So go to papers. I had a couple other papers published in 08. This is International Journal of Green Energy. Here's the online version. And one more thing before we dive into this, I just want to go over the syllabus one more time, because apparently, and I'll just do this at the start of every lecture, let you know what to do. All of the due dates are on the syllabus, at the bottom of the syllabus. So right now, we are at the end of, we're nearing the end of week 3. This is Thursday of week 3. So I would love it if you turn the summary in today, because it's due today. But as we know, as we saw last time, it's impossible to have anything due at exactly one moment in time. Time doesn't really, well, some people claim time is chopped up in little moments. But it would be bizarre if everybody turned in their assignment like at exactly the same time. So you have a window of opportunity to turn in Summary 1. That window starts today. It's right there, ready to be turned in, and it closes during week 4. So just get it turned in before lecture starts on Tuesday morning of week 4. That's when Summary 1 is due. It's due in that window. Okay. Now, let's look at the paper. Like I mentioned, this paper took, well, it took 4 years to write, and, well, it took a couple years to write and a couple to get published. As I mentioned previously, I tried having it published in a couple different journals, and we can find those. Energy and Environment Journal.
Was that you down there rowing?
Yeah. Mm-hmm. Yeah, I used to, I was on the U.S. rowing team for a few years.
Oh, wow.
Yeah.
Nothing big.
No.
Ah, yeah.
Yeah.
It's whatever.
Oh, nonchalant,
Yeah,
yeah.
it just mean you were good at it?
I was good enough. Yeah, I was good enough to compete internationally.
Yeah.
Yeah. So here's the paper, published 8 times a year. 2015 is volume 26, means they've been publishing it for 26 years. I submitted my paper, in I don't know when it was, 05 or 06, and it was not even reviewed. They said this is not the type of publication we're interested in. I also sent it to another journal called Energy Policy. So this is, and Elsevier, you'll notice, is a publishing house. They keep, they publish a lot of different journals. Just happens to be one of them. Energy Policy, I did the same thing here, and they just simply sent it back without review. They said, we are not interested in publishing your paper. And at that point, I'm like, what's going on? Why would you not even review a paper that I spent 2 years writing? And at that point, I sent an email to, are you friends with Diamond? Well, he probably would not
Colleagues.
know me. No, I wouldn't say we're friends or colleagues. I am friends, or at least acquaintances, with one of his colleagues. There's a Chris Filardi lives here in Missoula, and he's co-authored papers with Diamond. And so at that point, I just emailed him and said, I've read a lot of your work, and why would it be that these two journals would not review my paper? They said, well, the journals are not really about renewable energy. This is not what they do. It looked at that point that there might be some sort of political bent or twist or bias or what have you. Jared Diamond coined a phrase called the photosynthetic ceiling. And, you've probably heard of your carbon footprint. That's sort of, looking down. You can also think of your photosynthetic ceiling as looking up. Where does our energy come from? It comes from the sun. And at the time, if you would have Googled this, maybe, what year is it? 2016. If you would have Googled this 10 years ago, you might have gotten 10 hits, maybe 100 hits. And I did so about 6 years ago, and the number one hit was actually from one of those two journals. I can't remember which one it was, Energy Environment or Energy Policy, just blasting Diamond and saying he's wrong, he doesn't know what he's talking about. So they spent more time and more words or sort of defying him or
Going against them?
Yeah, anyway, so the photosynthetic ceiling, basically, and we can just kind of draw it out like so. If we get into Energy 102 in the spring, it basically just says that, here we are, here we are on Earth. Here's the sun. And, all of this electromagnetic radiation, I'm just going to put in a phi for photons, and we did this in class a couple weeks ago. It's been hitting the planet for 3 point whatever x billion years. Photosynthesis has been happening for quite some time. When the photon hits, and I'll show you exactly what it hits. I love this picture. Photosystem 1. Images. When a photon hits that thing,
What?
yeah. So that's a protein that sits inside of plants that build themselves with sunlight and CO2. Yeah. When a photon hits that protein inside a plant, it splits a CO2 molecule. Oxygen comes out one side, carbon comes out the other side, and the plant builds itself.
Respiration part of it or whatever.
Yeah, respiration is part of the metabolism, but this is just direct photosynthesis, taking one photon. Well, what happens, and so I'm just going to put in PS1, photosystem 1, and that's sitting in all, and there are, well, I don't want to say countless, but Avogadro-sized numbers of these things in individual plants, and Avogadro-sized number of plants on the planet. What ends up happening, an electron gets activated, and once that electron is activated, it can then form, start to form carbon bonds. And that's basically it. And so the photosynthetic ceiling says that there's a finite amount of sunlight that hits the planet. I think we talked about a little bit that right now, civilization is running at 16 terawatts. This is in your textbook as well. That's our power rating. And that if you sum all of that power up over the year, the little graphs that I gave you last time, that's 500 exajoules of energy per year. Okay. Now, this sunlight is hitting the planet about 10,000 times faster than we can use it. But are there plants everywhere absorbing that? No. Are plants 100% efficient at converting photons into carbon bonds? No. Are there solar panels everywhere? No. A lot of it's just wasted. Bounces off the desert, bounces off of a mountain, bounces off the ocean, whatever. Some of it's absorbed. So the photosynthetic ceiling says, at what point does this number start to approach that number? You go far enough back in time when there were, let's just say there used to be, 1 million humans on the planet. And there was one fine day back in history where that's all there were, 1 million humans. Cross that threshold. Now, those 1 million humans, and we covered this a little bit already in chapter 3, they were eating, maybe they had some fire, maybe they had domesticated horses. You could call a horse a technology, if you will, if you bridled it and made a saddle for it, and now it's sort of under your control. If we multiply that, and let's just say that each human is running, and each one of us are running at about 100 watts. And let's just say, gosh, on average, we might have a fire and maybe a horse that was sort of shared among us. And let's just say shared among us, it might have been an extra couple hundred watts, something like that. So 1 million times 300, there's 3, and then there's 1, 2, 3, 4, 5, 6 zeros, right, for the million, and then a couple more for that 300. We would have been, and this is watts, so 1 million people times 300 watts. What is that? Giga? Oh, you know what? Hang on. Let me be a little more careful with that. Take 1, 2, 3, 4, 5, 6, 7, 8. There we go. No, I had it right.
Yeah.
Yeah, that was right. Yep. Equals 300. What is that? That's just megawatts.
Mm-hmm.
Coal strip 4 runs at 300 megawatts. So just that one, a quarter of coal strip was all of civilization at whatever point in time that was. Later in the course, we'll sort of look and see whether or not we've actually sort of peaked. Is this 16 terawatts a peak or not? Another way to think of that, besides the photosynthetic ceiling, is what's called the Kardashev limit. Kardashev was a Russian physicist, scientist back in the 60s, and it kind of gets back to this picture that I was just drawing. Here's our star, there's our planet. Kardashev said a type 1 civilization can use and store energy which reaches its planet from a neighboring star. A type 2 civilization can harness all of the energy. So somehow and we're far from that. But you can sort of think of the Kardashev type 1 civilization as the same as a civilization that has reached the photosynthetic ceiling. So those are kind of the big picture things that I was after.
You think Carl Sagan used to reference this?
Sagan probably did. Yeah, he probably
He
did.
uses it all the time.
Yeah.
Because some of his more out there
Yeah,
theories.
yeah,
With
yeah.
the solar panels being discussed, some over in Europe are using solar panel, experimental solar panels for sidewalks.
Okay, I've heard this, solar panels embedded in sidewalks.
And
Yep.
or in the street
Yep.
as well.
Yep.
So there's some country that just enacted so many blocks of it as
Mhm.
an experiment. I can't remember what international
Yeah.
country it was, but
Yeah.
it's already started.
Yeah, well, it makes sense, because otherwise, what's the sun doing? It's just bouncing off there, it's just waste.
Yeah.
There you go.
France is building a solar highway.
Yeah, well, this one is this a couple few blocks downtown
Yeah.
in some countries, just kind of
Yeah,
But I was just excited because how much that can produce, you know.
Oh, yeah, yeah,
It's like,
yeah.
it's free.
Well, you talked about that here in Nevada too, weren't you?
Yeah, I know Nevada's big on concentrated solar in addition, so.
They talked about being able to power their houses up just off of their streets that they would
Oh, yeah,
build.
yeah,
Yeah.
yeah.
And it would just, all branch out.
There is no shortage of sunlight, we'll put it that way. Yeah. No,
Not
no,
Nevada.
yeah, no.
Renewable source.
Yeah. So let's just do this problem. What I'd like to do for today's problem, as promised, is I would really like us to try to derive, and just, do your best on this. Do your best on this. I'd like you to try to derive where this comes from. Because we just, we're talking about energy density of gasoline versus diesel. We'll get into that more in I think it's we'll get into some of the physics in chapter 4, and then we'll get into some of the energy densities, different energy types. I think it's chapters 5 and 6. Yeah, we'll get into motive power, it's 5 and 6. But I would like everyone just to sit down and see if you can derive this. And it's going to be a challenge. I'll kind of walk around. I'm going to pause the recording and walk around, but because this was a big sticking point for this paper. How can you measure sunlight on a volumetric basis? Because typically sunlight is measured this way. So I'll give you a couple things to start with. This is a great picture to start with. Typically, let's just look at a little patch of Earth now. This is 1 square meter. And what we're looking at in terms of power density is about, and we'll just keep the numbers simple, is about 1,000 watts per square meter. And if you go into the solar trades, you'll use this number all day long. So that's one number to work with. You got 1,000 watts per square meter, and there it is. And where's it coming from? Well, here's the Earth. Here's the sun. This square meter, it started somewhere here in the center of the sun. Another thing to note, I just learned this a couple of years ago. You're asking me if I watch TV much. I tend to just kind of watch YouTube videos of physicists and things like that. I did have the pleasure of seeing Neil deGrasse Tyson speak live in Michigan here last March. And he's kind of the new Carl Sagan, if you will. He did Cosmos. And one thing he mentioned is that the photon that takes 8 minutes to get from the sun to the Earth, so delta T equals 8 minutes. That's the travel time of the photon from the sun to the Earth, 8 minutes. And it's what's the speed of light again?
It's like 156,000
Miles per second. I think it's 300 million meters per second. I think that's it. 300. We'll check that in a second. 300. I used to be really good at remembering all these numbers, but I'm just not anymore. 300 million meters per second. We'll verify that. That's the velocity. And from that, we can calculate the distance to the sun, because we know that the velocity equals the distance divided by the time. So I gave you the time, I gave you the velocity. From that, you can calculate the distance. Now we know the approximate distance from the Earth to the sun. We can put a number in there. And we know that we've got, again, that 1,000 watts. And I'm just going to try to draw like a prism from the sun to the Earth. So just imagine that 1 meter square is sitting there on planet Earth, and this prism is going all the way to the sun, however long that is. Oh, and to finish my previous Neil deGrasse Tyson thought. It takes that poor photon 9 million years to get out of the center of the sun. And then it takes it 8 minutes to get from the surface to the Earth.
Does that do all the reactions?
That's a traffic jam and a half, yeah.
Traffic jam.
And, I don't know, I'm sure there's way more details than that. I mean, probably that photon's getting, absorbed and resplit, and there's, fusion reactions going on there. But talk about, takes it 9 million years seems like a long time, but the sun's, a few billion years old, so it's just a thousandth of the sun's lifetime. But yeah.
But how do they know that?
Patience.
Yeah, math, physics, a lot of time in school, yeah, patience,
Pythagoras.
yeah.
Does it take 9 million years to learn it?
Yeah, no, I don't know. But, and you know what, and also, that's an average. Typically in physics, you're dealing with statistics. That 9 million years is an average. And really, it has no relevance whatsoever to this problem we're trying to solve.
We're also thinking of a smaller scale version blown up to the entirety of the sun. So maybe that same reaction happening in a smaller
Yeah.
scale blown up.
Sure, yeah, and we can now in nuclear reactors and nuclear colliders create temperatures and energies that the same as, so they can, to some degree study it, verify that with on Earth.
Amazing that they can do it.
It is, no, it is, it really is. So what I'm going to do is get from this number, 1,000 watts per square meter, and I want to get to the energy density. I want to get to joules per cubic meter. And I think by now we know that volume equals area times distance, or times height, however you want to think about it. That's how volume is calculated. And we know that energy equals power times time. So you've got energy as power times time. You've got volume as area times distance. You know how far it is to the sun from the relationship between velocity, distance, and time. And what I'm asking to do is come up with this number, 1.5 microjoules per cubic meter, using the numbers I just gave you. So I will.
Go back over to that.
What's that?
Can we go back over
The drawing, absolutely. Yeah, I'll keep that up. So I'm gonna pause the lecture. I think I've given you everything you need here to solve it. And at this point, well, also this little v is velocity, and this big V is volume. Big V is volume, little v is velocity. Okay, I'll pause. I'll let you struggle, and then we'll solve it. Good, we're in good timing right now.
Trillions of miles.
Yeah. Okay. So we've reached the level of sufficient irritation. It's time to solve the problem. Good. Perfect timing. Yeah. Okay. So what we're working on here. Let's just first get the distance from the sun to the Earth. 93 million miles. We're going to do everything in SI units, just so we don't have to really play around with the units too much. So we'll take that equation, turn it around. Distance equals velocity times time, right? We have the time, we've got the velocity, so equals, you understood that one, right?
No.
Well, let's just back up one quick second here. I can start with velocity. I'm starting with just velocity equals distance times time. I'm going to multiply both sides by time. Time. V times t, well, it's the same as, or t times v is the same as v times t, right? Just like
Right.
2 times 3 is the same as 3 times 2. D divided by t times t equals d. V times T equals D is the same as D equals V times T. Check?
Right.
Okay, I just skipped those steps. So, velocity, distance, velocity, time. Okay, so we got 300. Now we got meters per second. And then the time is 8 minutes times 60 seconds divided by 1 minute. So far, so good? Okay. So from there, we just have to, let's just multiply 3 times 8, that's 24. Let's just do it this way. So 3 times 8 times 6 equals 144. 144. Then we got 1, 2, 3, 4, 5, 6, 7, 8, 9 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9 zeros. Meters. 144 billion meters. That's going to be probably pretty close. We could go look it up. And if we get it wrong, we'll go back and check it. But this is how to solve the problem. Okay, so that's the distance. Now, what we're looking for is the volume of this four-sided pyramid. We just want to know how big it is. So we know that the volume equals the area times the distance or the height. Now, it would be exactly that if we were dealing with a prism, a stretched out cube. But in the case of a pyramid, you just divide by 3. You can fit 3 of those pyramids into the same volume as you could a cube. So we just divide by 3. And I told you the area, which was 1 square meter. And we just found the distance, which is 144 billion meters. So the volume equals 144 times, let's do it correctly, 1 meter squared times 144 times 10 to the, what is that, the 9th meters divided by 3. So basically we're just looking at 144 divided by 3 equals 48. 48 times 10 to the 9th cubic meters. So there are 50 billion cubic meters of space in that little pyramid between the sun and the earth. Okay, so that's the volume. Now, here's kind of the weird thing to wrap your head around. I drew this photosynthetic ceiling thing already with the photon kind of flying at the sun. This is it's kind of fun to think about. So right here on planet Earth, actually at the top of the clouds, if you will, something like 1,364 watts per square meter, and then like the clouds get in the way and the atmosphere, so by the time it gets to the surface, it's 1,000. But if you keep going back, everywhere along that same little slice, it's 1,000 watts. Where else is it going to go? It's not going to leak out into some other, neighboring pyramid. So to get the energy, I already gave you the power. So, it's 1,000 watts. And if we just go back and just imagine a big scoop where you go and just scoop all those photons up at once, you can get the energy. Imagine you could travel faster than light and just smash all those photons into one nice little pancake. Essentially, that's about what's happening in your solar panel. Like as those photons come smashing in, you're just squishing them in a nice little electron pancake. Yeah, photon pancake. So we are kind of doing that by sticking that solar panel in the way. Okay, so energy equals power times time. Yep, there we go. So equals 100 watts, or sorry, 1,000 watts, times the 8 minutes, 60 seconds per 1 minute, equals, what's that, 48, triple zero, quadruple zero, 1, 2, 3, 4, joules. So they're, that might look like a lot, but it's not. I'm just going to round things up a little bit. I'm just going to say this is 500,000 joules. That equals 500 kilojoules. That equals, gosh, 0.5 megajoules. That's like a half hour of energy for you, because each one of us consume 10 megajoules of energy per day. It's not much. You know, that's not going to, I mean, so even though that's a long distance, you sum up all those photons, it's not a whole heck of a lot.
It happens every 8 minutes, though, right?
Every 8 minutes, yep, every 8
And
minutes.
that's in a meter square.
In a square meter, exactly right. Every,
Square meter ain't that big.
not that big. Okay,
But
so
that prism getting here is big.
prism getting here is pretty big.
Yeah.
Well, on a solar system scale,
Not-
it is.
no, it's not.
Yeah, big's a
It
weird
depends
relative
on
term,
you look at it.
exactly, yeah.
How you
So,
look at it.
so energy per volume is this. It's, well, let's just do it this way. Let's just do it in joules. So it's 5 times 10 to the 1, 2, 3, what's that, 8th? 5 times 10 to the, no, what am I doing here? 5 times 10 to the 5th. Yep, 5 zeros, joules, divided by, and I'm just gonna say this equals 50 times 10 to the 9th meters squared. So that'll just turn into 5 times 10 to the 10th meters, cubed, sorry, meters cubed. Now, I can see right away my number's not going to come out exactly as I wrote it in the paper, and I kind of rushed through this, but the point is, it's small. So we've got 1 times 10 to the negative 5th joules per cubic meter, and a millijoule is, so it's going to be equals 1 times 10 to the negative 2 millijoules per cubic meter. Sorry, I'm getting down to the bottom here. Let's start a fresh page. 1 times 10 to the negative 2. How many microjoules is that? So let's just write it out a couple different ways. So 0.1234 joules per meter cubed equals 1, 2, 3 millijoules. I have to do it visually per meter cubed. And if we move that 1 over 1, it ends up being 10 microjoules per cubic meter. What did I say in the paper? 1.5. Well, so somewhere I somewhere I was off by almost a factor of 10. But,
I think it was, you missed this, the zero when you times in that energy part.
Yeah.
1,000 watts to 8, and then I think you forgot to add in 60. Or no, it's in the top one, the D equals V times T. When
Oh, really?
You forgot to add that zero of the 60. I'm pretty sure.
well, okay, let's just try it. Let's give it a quick shot.
Oh, yeah.
Equals 300 times 8 times 60. No, I think that's, well, I think that number's right. Well, so there's either a small error in the paper, or I just, made a small error. The point is, that's how you run that type of calculation. So just to recap what we just did, we, what we did, we imagined and if you want to go back and rework this and find out exactly where that decimal error is,
I'm not too concerned.
well, and I can, and I know I've got the hard copy back in my previous notes. But the point is, we know what the power flux is, the power density of sunlight hitting the Earth. We know how far it is from the Earth to the sun. We know it takes 8 minutes for the photons to get here. So effectively, what we did, we just looked at how many photons there are per cubic meter. And we can compare that to how many joules there are, and let's just do that now in the paper. We can go down here. And compare that to how many other joules there are per cubic meter in other energy sources. So here, here it was 1, 2, 3. Yep, put the decimal there, that's 1.5 microjoules. Geothermal, as it turns out, the Earth also radiates. Why does it radiate? Well, because the Earth is warmer than outer space. Anything that's hotter than something else around it is going to radiate away. And I think the Earth is radiating at something like 60 milliwatts per square meter on average. Obviously, it's more if you're near a volcano, less if you're out in the ocean, but on average, you can do the same thing, and then just sort of start digging down. Where does that radiation come from? Well, it comes from the fact that the center of the Earth is warm. It comes from the fact that there's leftover friction from earthquakes, etc. Everyone, rub your hands together. They get hot. Same thing happens when rocks rub together. There's some geothermal, and yeah, when the Earth was formed, it was big collisions of large, massive objects smashing into each other, and that same thermal energy is still here. Yeah.
How would you account the current status of like magma plumes beneath the Earth? Do you think the sun would have some way of adding to the energy that would be created?
Oh, so does the sun's energy add to? Yeah, it does. The sun's electromagnetic spectrum is very broad, and some of the photons that come out of the sun, well, some of them pass right through the Earth. Some of them, yeah, would be absorbed by the deeper layers. So
2012.
yeah, what's that?
2012, the movie.
Oh, I don't know.
It's
Protons are heating up the Earth's core,
Okay,
and so you have mass crustal displacement.
right. Yeah, there's another movie called The Core. Yes, there's a lot of those. Yeah.
But, because I was a well-set geologist, if you go down 10,000 feet, you're looking at a temperature of like 280 degrees,
Yeah.
just 10,000 feet down.
Yeah. Cool.
It's strange because just below the Earth's crust, it's lesser.
Yeah.
Well, that's like where you can use like food storage, like if you dig down.
Yep.
Yeah, well, it's really cool thing about like water, like ponds and stuff too.
Yeah.
Well, if the energy technology program survives, you'll be able to take Jonathan Bowe's geothermal course next fall. We'll see. Okay. Do the same thing for wind. He goes, wind is similar to sunlight, but instead of, radiation blowing past you, you've got air molecules blowing past you. And this is just kind of an average, wind at 10 miles per hour. Tidal power, can vary, depending on where you are, but that's kind of a range. Human power, I just sort of said, well, we're running at 1,000 watts. Our body's volume is about 1/10 of a cubic meter. So there you go, one human power. And it makes sense. Like, yeah, I can stand up against the wind. I can stand out there in the tide as long as it's not concentrated, and I can sure stand up to solar too. Now you start to get into oil and gasoline, and here's where that controversy came up when I wrote that, because the gasoline energy density is almost equivalent to oil. And you can see I only used one or two significant digits because you can argue about octane ratings, et cetera, et cetera. The reason I use such a small number for oil, or for gasoline versus oil, is once you put it in the car, the majority of that energy turns into heat. So this is the mechanical energy density. This is the thermal energy density. Okay. And then these are all pretty well known. That's how energy dense food is, natural gas, et cetera, et cetera. I also tried to show that whether or not the car, and this is sort of an argument, if you will, for carpooling, the energy density doesn't really change a whole lot if you just add a few humans to it, because they're not really contributing.
What does methane do to that factor?
To what?
The methane that they add to the gasoline?
Oh, ethanol?
Yeah.
I've never heard of methane being added to gasoline, but ethanol will reduce the energy density of gasoline. Because ethanol has that oxygen molecule on
And then it
it.
just doesn't burn, it's not really.
Does not burn as hot, that's correct. Okay, so, read through this, there's a lot more in here. And like I said, when you're running when you're doing your summary, just pick out a few key paragraphs that sort of struck home with you and focus on those. You're not going to be able to summarize the whole paper. Just say, I was the most interested in the geothermal or in the human or et cetera, and that's what you're going to write about. Okay, we will take a very quick break, and then we'll just get through chapter 3. Just a few more things to show there. I went a little longer than usual. I usually try to keep these to 30 minutes, but that's okay.